Well, hello, welcome again to our journey into complex analysis. And we introduced the complex line integral in the earlier section, and we want to now have a look at the idea of primitives, because we'd like to see if there's some nice analogues between what we know in the real world and what happens in the complex plane. We defined the line integral in terms of a Riemann sum, and then we found a nice formula for calculating it by parametrization. And I want to see if there's an alternative to doing that. So we say a complex function has a primitive g if g is analytic and g dashed is equal to f. Now our main theorem here is if f is continuous on a domain, that is an open connected region, which has a primitive g. Now that's the important thing. We're assuming that f actually has a primitive g. Then, if we take our two endpoints, be 2 points of D, and C be the piecewise differentiable path in D from ZA to ZB, then we can work out the line integral along C simply by taking a primitive, putting in the endpoints of our path, and subtracting. Just as a remark here, thus, exclamation mark, under these conditions, the line integral depends only on the endpoints and not on the curve itself. And you might like to compare this with what you know about integration along a contour in a conservative vector field if you've done some vector calculus. So this is very nice, but be very careful with the conditions. It says if f has a primitive, and we're not guaranteed it will have one. If f has an analytic primitive, then to work out the integral of f, we just need to find the primitive, put in the endpoints of the contour, and subtract. And that'll be contour independent. So firstly, we're going to assume that that C is a given differentiable curve, gamma of t, mapping AB into our domain. Then there's our definition. Our definition was we can replace the z with gamma of t, and we replace the dz with gamma dash dt. Now in this case we have a primitive, so the f is g dashed. So we now have g dashed of gamma of t times gamma dashed. But if we now think about the chain rule, this expression under the integral sign is just the derivative ddt of g of gamma of t. So by ordinary calculus applied to the real and imaginary parts, this integral then just becomes the evaluation of g of gamma of t from a to b, which is just the difference, and of course that's just g of z minus g of zb minus g of za. That is the difference in g between the two endpoints. Now that proves the first part of the theorem. In general, if the path consists of a number of curves, where gamma 1 up to gamma n, where zi is the endpoint of zj is the endpoint of gamma j, then by what we've just shown, we can split this up into integrating c along each of these curves, and then we can just apply what we've done, put in the endpoints and subtract. And of course we get a nice telescoping series which reduces us down to g of zn minus g of z naught. That is, that's the g of the endpoint minus g of the beginning point of the contour. So that's a very, very nice theorem, but of course it depends on g of f having an analytic primitive in the first place. That is the subtlety of this. So, just as an example, to redo that example we did before, we did the integral of z dz, where gamma is a path from 0 to 1 plus I, and we did that by parametrizing the path. We're going along the parabola y equals x squared. And because we can find a primitive of z, what am I going to do? I'm going to take z squared on 2 as the primitive, and z squared on 2 is analytic. So z in fact has an analytic primitive. There it is, z squared on 2. So Our theorem says you can simply think of this as a definite integral from 0 up to 1 plus I of z dz. Write down your analytic primitive of z, which is z squared on 2 from 0 to 1 plus I. Put in the endpoints and subtract, which gives me that. And when you expand it out, you get I, which is the answer we got before. Now, you will of course realise immediately that if f is continuous on a domain D and it has a primitive, an analytic primitive, and C is any closed path now, then because the beginning and the end points are the same, the integral along C of f of z dz is 0. Now this of course, again I stress, assumes that your function f has an analytic primitive in the first place. And the fact that it will have, provided f is analytic, is going to be a result coming up in the next section. Now we have a look now, while we've got our definitions here of these line integrals, we're going to be using this, what we're going to call the ML estimation lemma. Just as a way of getting your hands on what that might look like in the real world. If you go back into the real world and you just think of ordinary calculus, if I've got a function like this, defined on an interval AB, this is back in R, then you can get a very rough estimate of the area in here by saying, well, I'm going to draw the biggest possible rectangle I can draw that contains this area. Draw the biggest possible rectangle, and that's going to be this height here, and I'm going to call that M. And that M is going to be the maximum of, so this is our function f of x. So this is the maximum of, just in case f went negative, I might take the absolute value of that. So my M is the maximum of, I'm going to take the maximum of this for x on the interval AB. And I'm going to let L be this length here. So L is just going to be B minus A. L is B minus A. And then we can say, well, look, the area under the curve, AB f of x dx, is going to be less or equal to the area of this rectangle. Now the area of the rectangle is just the L times M. And so that's what's happening back in the real world. All I'm doing, I'm just taking a very rough estimate of what the area is by surmounting it by the biggest possible rectangle, and then I can say that the size of this integral, just in case it went negative, I can say the size of this integral is less or equal to ML. And we'd like an analogue of this in the complex plane, and in fact we're going to need this much later on when we start looking at various real improper integrals. This ML estimation lemma is going to be quite important, and it's useful for a whole range of things as well. So we're going to try and generalize this idea from the real world into the complex plane. So, and I'm going to call this the ML lemma. And I said you might compare it with a function is real and the contour is an integral. So I'm simply going to go back and use the triangle inequality, or generalized form of it. We're going to say that the sum, I equals 1 up to n of this expression here, is the modulus of this is less or equal to the sum of the moduli of each of these, and I can split these up. So if f is bounded in modulus on C, then I can write the modulus of f of z is less than m for all z on the contour. And then we can simply say this is less or equal to m times the modulus of the delta zi's, and I can take the m out the front. if we take a limit then as the delta zi's go to 0, then this quantity here is going to be simply adding up all the little bits along our contour, and that's going to approach the length, L, of the curve. Assuming that such a length is defined, and the technical name here is we assume that the curve is rectifiable. Well, if it's continuous and differentiable, then it will be rectifiable, so that all works nicely. And thus we have this analog that the modulus of this is less or equal to m times L. The modulus of the integral is less or equal to m times L, where m is the maximum modulus of f on C, and L is the length of C. And as a little example, we're going to show that the modulus of the integral of z on z squared plus 3 for mod z equals 3, so we're on a circle, centre of the origin, radius 3. The maximum this can be is only 3 pi. So here's our function f, which is z on z squared plus 3, and our gamma is mod z equals 3. So that's just a circle, radius 3 in the complex plane. So there's our C. Now the for z on C, let's have a look at the denominator firstly. We've got z squared plus 3, so that modulus, using the second triangle inequality, this is bigger or equal to the absolute value of the modulus of z squared, which is the modulus of z all squared, minus the modulus of 3, which is just 3. Now, if z is on our contour, then the modulus of z is just 3, so we get 3 squared is 9 minus 3 is 6. So when I then turn this upside down, 1 over this is going to be less or equal to 1 over 6. So the modulus of z over z squared plus 3 is less or equal to modulus of z is 3. The bottom 1 over this we said was less than 1 on 6, and that's a half. And there's my m. Now the length of the contour is easy. It's just the circumference of the circle, radius 3, so that's just 6 pi. So the modulus of the integral is less or equal to ml, so that's a half times 6 pi, which is 3 pi. Now the final example for this bit, I've put it as a challenge problem, but I'm actually going to work through it because it is a very important problem. We're going to be using this idea later on in the material when we start looking at real improper integrals. At the moment it looks a little bit strange, so let me just tell you what it's saying. At the moment we have a gamma in the upper half plane, so in fact we want it to go this way, don't we? So we have a semicircle around here of radius r, and I'm going to assume r is bigger than 1, just to make things easier, because in the limit we're going to be taking r going to infinity anyway, so we may as well assume our r is bigger than 1. So there's my gamma. It's just this semicircle here. And we're going to show that if you take the integral of e to the 2iz on z to the 4th plus 1 dz around this contour, well, you'll get some complex number. And then as r goes to infinity, as we blow out r to infinity and the semicircle gets bigger and bigger out to infinity, then, interestingly, the value of this integral disappears. It goes to 0. Now we're going to use this later on because we're going to be working out integrals along the real axis, and the way we're going to do them is we're going to work out the integral from minus r to r, and we're going to add in an extra piece around here, and we're then going to see that as r goes off to infinity, the value of the integral along this extra piece vanishes. It goes to 0 for us, which turns out to be very, very useful. Okay, so how do we prove this result? Well, here we go through. Here's my f of z. It's e to the 2iz on z to the 4th plus 1. For z on gamma, then I have to work out the maximum modulus. That's always the tricky bit. I've got to work out the maximum modulus of f for z on gamma. So the modulus of 2iz, I've got to put z as x plus iy in. So I do that, simplify. Now this is the modulus then of 2 to the ix is just 1. I can split up the moduli into 2 bits. The modulus of that is 1, and this is just real, so it's positive, so this is just e to the minus 2y. Now remember, if we're on gamma up here, the y values are all positive. And if you think of the graph back in the real world of e to the minus 2y, and if y is bigger or equal to 0, then this is less or equal to 1. So that's good. We can bound this thing out by saying on this contour gamma, its modulus is less or equal to 1. For the bit in the denominator, we use again the second triangle inequality. So this is bigger equal to, it's z to the 4th, modulus of z to the 4th minus 1 absolute value, and I can pull the 4 outside. And if we're on gamma, then the modulus of z is r, so this is r to the 4th minus 1, and that's why I wanted r to be bigger than 1, so I didn't have to worry about this being negative and taking absolute values and so on. So the maximum then of the modulus of f of z for z on gamma is less or equal to 1, that was from the e to the 2iz, over r to the 4th minus 1. Now the length of the contour is easy, it's just the circumference of a semicircle of radius r, so that's pi r. Plugging all that together then, the size of the integral is less or equal to, well, pi r was my L, and 1 over r to the 4th, 1 over r to the 4th minus 1 was my M. Now you can see the dominant term on the bottom is r to the 4th, there's only an r on the top, so that's going to go to 0 as r goes to infinity. Now that means if the magnitude of the integral is going to 0, not infinity there, if the size of the integral is going to 0 as r goes to infinity, then that means the value of the integral itself must be going to 0. And that means the limit as r goes to infinity of this is equal to 0 as claimed. And that is the end of this section.